topic is about optimal control for PDs. This is the main topic, and the title is a little bit different, so it's just a little bit more specific. So I'm going to talk about dynamic programming principle on a tree structure. So we will see throughout the talk how it works. And the setting is a finite horizon of optimal control. So this is a joint work with Maurizio Falcone and Luca Saluzzi. Both they are in Sapienza and Rome. So before starting with the math, I'm going to try to quickly explain what is an optimal control problem. So, and I give you an example. The classic example is can be the Cart-Pendulum. So yeah, you see that you have a cart which is just moving on the horizontal line, and attached to this cart there is a pendulum, and it's clear that as soon as the cart starts moving, the pendulum falls down. And this is actually the natural behavior of this model. So behind this model there is a differential equation, a system of differential equation dimension 4 here, and this is the natural behavior. Our goal is to modify the natural behavior, introducing a law which is called control, which helps us to keep the cart at the original position and also the pendulum attached so that it doesn't fall down. So the idea is here is that we have a model and we actually add an external source to the model in order that we can modify the natural behavior. In particular, we are not just interested in a general kind of control. We are interested in feedback control. And there you see, for instance, that, okay, we are able to get back to the solution, but also the control is able to react under disturbances of the problem. You see that here that we are just disturbating the system, and the control is always able to react and to bring to the desired solution. This is the idea of, let's say, a mathematical model, optimal control, and this one is about feedback control. So the talk will be about feedback control. Okay, this is the outline of my talk. First part, I will talk about classical standard dynamic programming principle and the Hamilton-Jacobi-Bellman equation. And then I will go to recent work based on tree structure. And if there is time, I will like to talk also combination with modeled reduction. Let's see how the talk goes and how fast or slow I am. Just feel free to stop me anytime. English, Portuguese, it doesn't matter. Really, just feel free to interact with me anytime. Okay, to set the problem into, let's say, more technical way, what we have, can you see the mouse here that it's like my pointer? Okay. So let's suppose that we have a differential equation. Y is my state, U is my control, and F is my dynamics. X here is going to be my initial condition. So this is the dynamical system. And in order to select the control, we have to provide a selection criteria. And the selection criteria is given by the cost functional that we are going to minimize with respect to U. And of course, Y should satisfy the differential equation. So my mathematical problem is essentially an optimization problem where we want to minimize the cost functional. This cost functional tells us how we want to compute the control in order to obtain our desired configuration. So in the case of the the Cart-Pendulum, our configuration is that we want to be close to the origin. So for instance, the norm between the state should be minimized, because that is the distance from the origin and the state. since we are interested in particular in feedback control, I also defined another important tool, which is called the value function, which is the value function. And the value function is the infimum with respect to the control of the cost function. So we have a differential equation, a way to select the optimal control that we are going to minimize, and we have the value function. So let's suppose that we are able to compute the value function, then we straightforward are able to compute the control. And you see that the control in this case is given by the argmin of this right-hand side, which is called Hamiltonian, where you can see that we have the value function, the gradient of the value function actually here. We have the dynamics, okay? And then here we have the running cost. So the running cost, I mean, the function inside the integral of the cost function, okay? So now what is the problem is that we have to compute the value function. How can we compute the value function? One way to characterize, also let me mention that here I'm working on a finite horizon, okay? So that my time horizon is finite. A way to characterize the value function is given by dynamic programming principle, which is due to Bellman in the 60s. And this is an implicit way to characterize the value function, which is given here. And essentially, what does it tell you, the dynamic programming principle? Basically, we let the system run up to time tau with a given control. We then correct with the best we can do, because actually this is the value function. So the value function is the best we can do at the position y of time tau. And then we minimize with respect to all the possible control. So this is the way to characterize the value function. Actually, that was taught in a discrete setting. And from the dynamic programming principle, we derive the so-called Hamilton-Jacobi-Bellman equations. You see, this is actually a PDE, and this is a time-dependent PDE, of course. This is a backward hyperbolic nonlinear PDE. Let me also mention that in this PDE, as you can see, you get all the ingredients of the control problem. Let's say you have the dynamics, you have the value function, which is actually the unknown part. You have the running cost, and you have lambda, which is a discount factor. Here we need to have the final condition, which is also given. So the key fact here is that in order to get the feedback control, we need to solve a nonlinear PDE. So we started from an ODE, okay, which is y dot equal f. We ended up to a nonlinear partial differential equations. What is the dimension of this Hamilton-Jacobi-Bellman equation? The dimension is the same dimension of the system of differential equations. So with the difference that imagine to have a differential equation dimension 4, now we get a PDE dimension 4. So the solution of the Hamilton-Jacobi-Bellman equation is not trivial, and for that we need to get some numerical approximation. One way to compute a numerical approximation is a straightforward application, a straightforward discretization of the dynamic programming principle, which is actually given here. So n stands for time, and for instance, this part is the discretization of the integral, and here we have, remember that here we have v of y of tau. So tau is this is valid for any tau, so we can choose a small tau, for instance t plus delta t, okay. And then here this is one approximation of the differential equation. So we can use an Euler method here. If we just have t plus delta t This is the initial condition. And then here, this is one step of the Euler method to approximate the differential equation. And then we evaluate the value function in this point. Okay, remember that here the dimension of this problem is has the same dimension of the differential equations. But then if we think about a solution of a PDE in high dimensions, and we have to build a grid, that is almost straightforward to see that we have the cars of dimensionality. Imagine that we have, let's say, 0, 1 as a domain in dimension 10. We use 10 points in each dimension. We get 10 to the 10 points to discretize this problem. So this is basically unfeasible. So one problem with this method, this is the discretization on this method is the cars of dimensionality. Another problem is that we have to constrain this problem to a numerical domain, which impose us to select some boundary conditions, which of course they slightly modify the problem, so they are not natural. And also, whenever we want to compute this term, so we ended up in a point which might not be on the grid. So for instance, if we start from xi and we get some discrete control, here you see that it might happen that we don't go to a point of the grid, but somewhere inside the domain or outside. So if it is outside, we have to select some boundary condition. If that is inside, we have to perform an interpolation operator, which for high-dimensional problem, this is also expensive and not trivial. So I would say in the last 10 years, there is literature on this problem, especially because my idea is that I want to apply this problem to a partial differential equation. So my y dot equal f will be a partial differential equation. And this is easy also to see that if we discretize a partial differential equation, we have a large system of ODEs, and that is almost impossible to solve with the classical techniques. So here there are some ideas that have been people have been working on. So what is in bold here is that is where I gave some contribution. For instance, this is a coupling of about two methods, which is value iteration and policy iteration, and at least we can get a speed up in the approximation of the value function. The classical domain decomposition in order to get smaller domain and have less degrees of freedom. Model order reduction, which is a way to reduce the dimension of the problem by means of orthogonal projection. If there is time, I'm also going to talk about this method. I'm currently working with my PhD student, Hugo Oliveira, on the use of radial basis function as interpolation operator here in this method, because the radial basis function are very useful, especially for high-dimensional problem, so that end with a scattered mesh. So we don't need a structured mesh to solve the problem. Spectral methods, also tensor decomposition have been involved in the approximation of the value function, and the tree structure algorithm, which is actually the topic of today's talk. So if there are any questions on the settings, but then I'm going to give more details on this algorithm. Okay, looks like there are no questions. I'm not sure if there is a chat and someone is chatting something. Okay. So here there is a list of references for this talk. There is a first paper appeared in 2 years ago now in Science Journal Scientific Computing. Then we have a proceedings where we did some high order approximation. Also, we have used this method of the tree structure with model reduction in applied numerical mathematics last year. We also have done optimal control with state constraint and error estimate for the man. So this is the 5 references if you are interested. Now, of course, I mean, you can feel free to contact me if you want the paper or you just want to discuss something. So what is the idea? What is the idea of the algorithm? So first of all, we have to start with an initial condition, which is given. And then we get the control set. We have a discrete set of controls. We discretize the control set. So you see here we have some constant terms in a range, okay? And then what we do, starting from the initial condition, we compute all the possible, let's say, direction for a given constant control. So we pick UI, and then we compute x plus delta tf for a given UI. So just a remark, this is the Euler, explicit Euler approximation of the ODE. So just for at the moment we are working on the differential equation, okay? So at the first stage, we have an initial condition, and then from the initial condition, we compute all the possible trajectory for different, for a different number of discrete controls. Then we keep working on that. So let's say this is the zero level, okay, the initial condition. This is the first level. Then from the first level, for any point of the level, we do the same. So we suppose that this is the new initial condition somehow, and we compute all the possible direction for different controls. Now, it's easy to see that we have a tree structure. So because this is iterated, and here it's very important to have a finite horizon. Okay, so now we have a tree. So this is essentially our grid, which is not structured, but we have some flavor about the dynamics of the differential equation. Then after that, we build the tree. We can compute the value function. Of course, we discretize the time, and then formally there is basically no difference with what I've shown you before. But now we just compute the value function on the trees, on the nodes of the trees. So in this way, essentially, we get rid of the structure grid, and we just compute our value function on the nodes of the trees. So you see that this approximation has no difference with what I've shown you before. The only huge difference is that we are using a tree structure for our grid. What are the pros of this approach? So first of all, we don't need an interpolation operator, because anytime we do one step of the Euler method, we fall on a node of the tree, because this was pre-computed. Of course, I keep assuming that the control set is discrete. Then, in case the dynamics is autonomous, actually we can compute the value function for more levels, and also we mitigate the curse of dimensionality. We can solve this problem for higher dimension. I think we have done simulation for 1,000 dimensions, something like that. Just to give an idea, till 10-15 years ago, that was possible to solve this equation up to dimension 4. Now we are doing lots of work on this mitigation. Of course, It doesn't solve the curse of dimensionality, but we get something which is reasonable also for higher dimensions. What is the big problem? The big problem is that is the cardinality of the tree. So the cardinality of the tree increases exponentially. Why exponentially? Because this is order of the number of controls to the number of time steps. Okay, now, so we pass from the curse of dimensionality to the problem that the tree increases exponentially. But this is, let's say, without a dimension. So that does not depend on the dimension of the problem. So the dimension of the differential equation. So what can we do? So we have a tree. If there are too many branches, we can cut the tree. Why we can do that? So first, how we can do that? If there are two nodes at the same level of the tree, very close, we can cut one of the two nodes. Why we can do that? So imagine that. So here you see that we have the tree. Okay, this one is very close. Let's say the red one is very close to this one. Okay, so this is at level n. So then, according to this criteria, we can cut this node. Why we can do that? So it's well known that the value function is Lipschitz continuous. So that means if two nodes are very close and the function is Lipschitz continuous, the error that we get neglecting those nodes is very small. So for this reason, we can cut a node of the tree. So this will be helpful because we can also mitigate the problem of the exponential increasing, the exponential cardinality of the tree. So we also have some error estimates. So there is old work by Falcone and Giorgi where they were able to provide error estimates of order square root of delta t. With our work, we were actually able to prove that this is order 1. So what does it mean that we have order 1 here? That is essentially the same order of convergence of the method that we are using in approximating the differential equation. Because here we are using forward Euler, which is order 1, so big O of delta t. And here we get the same order of convergence for the value function. This also suggests how to choose the pruning criteria. So if we choose something which is below delta t, for instance, delta t square, we know that we don't lose accuracy in the approximation of the value function. Okay, so let's see some numerical results. So this is a two-dimensional problem where we actually know the exact solution, and when with the exact solution, I mean that we know the value function. So either there are some parameters that we are using. And so this is the tree. On the left, there is a plot of how the tree. So here, this is the initial condition that we consider, and you see how the cardinality of the tree is different. So here we have this is 10 to the 6, if I'm not wrong, and here it's 10 to the 4. So you see here that we gain at least 2 order for the cardinality of the tree, and the evaluation of the cost function, you see it's pretty much equivalent if we consider a classical approach, a tree structure without selection. So that means that we don't use a pruning criteria. And if we use a tree structure with a pruning criteria, you see that the curves here are pretty much on top of each other. So this is also expected from the estimate that we have done. So the big difference between using the pruning criteria and not using the pruning criteria is that we can go for a smaller delta t, as you can see here. So without pruning criteria, we were able to reach up to delta t 0.05. And you see here the order of convergence 1, which is what we, at least, I mean, there is that is a confirmation of the theoretical findings. And if we use a pruning criteria, you see that we can go down to delta t, okay? And we keep the same order of convergence. Actually, that was a suggestion of the error estimate. And you see the cardinality, how differs the cardinality. So just think about here 0.05 and 0.0125. You see that the cardinality here is still smaller than the cardinality here, but we don't lose accuracy, and we are able to keep the order of convergence. Actually, it's almost straightforward to apply to high order methods, because what we have found is that essentially the order of convergence depends on the order of convergence in the approximation of the value function is the same order of convergence of the method that we use to approximate the differential equation. So here we have used an OIM method, which is a second order method. Of course, when we go to higher order method, that increases the dimension of the tree. So here we were just able to get to 0.1 and having order 2. With a pruning, that you see that we're using something which is order of convergence plus 1. So here we expect order 2. So here then we set the pruning criteria to delta t to the 3. And you see here that, I mean, we have the order of convergence 2. Also here, there is a study with, this is always a comparison with the exact solution. Here it's a comparison using Euler method when we keep order 1. And actually, if we use a pruning criteria, which is not delta t square, you see that we lose the order 1 of convergence. And the same happens here for order 2. You see that the best is delta t to the 3. Okay, that was a problem in dimension 2, very small dimension, but that was very helpful for us to see and understand how things go. Now we switch to the control of PDE. In particular, here we are doing bilinear control of advection equation. So when we discretize the partial differential equation, here we have a problem of dimension 1000. So it's still not yet large scale, but it's very large. So the problem, the discretization of the problem, we have something which is with this structure. A is the discretization of the advection term, and here we have the bilinear control. Okay. The goal here is to track a desired configuration, which is given with the test. Okay. We penalize the control, and we have a final constraint. So again, what I want to stress is now dimension of the problem is 1000. So it's not a trivial problem where to do feedback control. So, and you see here, always using the tree structure. So this is so the y tilde means that our desired configuration is 0. So we want to steer the solution to 0. On the left here, we have the standard advection equation. So u equals 0. So this is the uncontrolled problem. And on the right, we get the control problem. You see here, I mean, it's happening what we want, that the solution goes to 0 fast. here we also have a comparison between one order method and two order method. So clearly, this is the evaluation of the cost function. So clearly, we can see that the second order method is better than one first order method. This is not surprising, but this is just a confirmation. And also, this is the final configuration of the advection equation. So you see here that we have, since we have a second order method, the uncontrolled problem is less diffusive. So here you see that the second order method is higher than the first order method, both for the uncontrolled case. But then when going to control problem, we see that the second order method is lower than the first order method. Of course, it's clear that both are working. I mean, they are going to zero, but as expected, the second order method is better. Then, for instance, this is also might be used to reduce the diffusivity of the problem. So when using finite difference method, it's well known that the advection equation has some artificial diffusivity. So now we want to, the desired solution is actually the solution of the advection equation. So this is the standard D'Alembert formula for the linear advection equation. So this is what we want to track, which is somehow a way to minimize the artificial diffusion that we have in the numerical scheme. And here you see that the second order method is better than the first order method. Okay, and the uncontrolled, you see how the diffusion, the diffusivity, the artificial, the numerical diffusivity comes into play. Also, in terms of evaluation of the cost function, you see that we gain one order if we compare first order method with a second order method. So again, what I really want to stress here is that we are able to solve, to control a PDE using Hamilton-Jacobi-Bellman equation. This is something that just 10 years ago was not even possible to think about solution of the problem, of this problem. So how does the cardinality change? So yeah, this is something curious, interesting, but there is no theoretically way to explain that. So for Euler method, the cardinality increases linearly. For the Euler method, which is a second order method, this increase quadratically. That was kind of interesting, but I actually have no explanation why that happens. Of course, we have to use pruning criteria in order to make it feasible. Any questions?
Alessandro,
Maurício, seu áudio está muito ruim.
Just a small question. In the first part of your talk, what was the particular equation and the particular functional you have used to make the simulations? I missed this.
Where about here? Maybe the first test, you mean?
Yeah, yes.
Here?
Yes.
Okay. So this is, let's say, x1 dot equal u and x2 dot equal x1 square.
Okay.
Very simple, but okay. we use because I mean the goal for us is control of PDEs, so high-dimensional problem. But in this particular problem, we know the exact value function. Okay, so also you see that the running cost is 0, just the terminal constraint is given, so it's a quite particular setting.
Okay. Thank you.
Any other questions? No. So how much time do I have? do I still have?
10 minutes, more or less.
Okay. Okay, I'll try to give an idea of. So the problem that I presented for a PDE, there was one-dimensional PDE, okay? And then we got into a problem which was, the discretized problem was dimension 1000, let's say. Now we want to go to two-dimensional PDE, control a two-dimensional PDE. So just to make it clear, so we have a PDE, special dimension of the PDE, we do discretization of the PDE, so we have a system of ordinary differential equation. The dimension of the differential equation is the same dimension of the dimension of the Hamilton-Jacobi-Bellman equation. Okay, so even if you think of one-dimensional PDE, then we have to think about discretization of the problem, and then we have the same dimension of the Hamilton-Jacobi-Bellman. So when dealing with the partial differential equation, as I mentioned, we ended up with a very large system, and one way is to use proper orthogonal decomposition, which is a way to decrease the number of degrees of freedom, or in other terms, to make an orthogonal projection onto a lower dimensional subspace. Here there is a list of people that have been working on this on the problem using proper orthogonal decomposition. So let me explain how proper orthogonal decomposition works. So again, imagine to have, so let's forget about the control problem. Let's just get into the dynamical system. So you can think this is discretization of PDE. I mean, I really don't mind. So this is a large system of these now. This is expensive to solve. So what we can suppose that there is an orthonormal base such that our solution might be decomposed into the orthonormal base times some coefficient. The dimension of the base here is L, which is hopefully way smaller than the dimension of the original problem. So L will be way smaller than N. So if we use the orthonormality of the bases, we get a low dimensional ODE. So now the dimension of this system is L, which is smaller than the original dimension. So now we get something cheaper. Question, how do we compute the basis? To compute the basis, first of all, we need some snapshots. Snapshots means that we have to solve the original problem for some time instances. Then what we want to do, we want to look for some orthonormal basis such that we minimize the distance between the snapshots and its orthogonal projection into those bases. The number of bases that we are looking for is just L, and in order to get few basis function. And if we want to solve this optimization problem, actually the solution of this problem is given by a singular value decomposition, where the first L columns of the left singular vector is the POD basis. So essentially the POD bases are given by a singular value decomposition, where we actually know the error. The error is given by the sum of the singular values that we neglect, and that gives an idea how to choose the number of basis function. Of course, the problem is snapshot dependent, so it depends on the data that we provide. So you can think about parameter problem, parameter dependent problem, optimal control. This, of course, pays out to do this this job. Then, if you consider the nonlinear part is still not completely independent from the dimension of the problem. And what is the problem here? That we have to project back to the original dimension, evaluate the nonlinear part, and then project. There is a list of people that have been worked on improving this method. The idea is to use an empirical interpolation method, where we just select some rows of this product in order to evaluate F, not everywhere. I'm not going to give details, but I just want to mention that I'm going to use this technique in order to speed up the evaluation of the nonlinear part. Okay, so then, provided that we know how to compute the basis function, if we want to use this technique in the optimal control setting, formally we do the same. We project our dynamical system. We get a reduced cost function. This is formally the same problem. And at the end, we also get a reduced Hamiltonian-Jacobi-Bellman equation. Now, what is the difference here? Formally, there is no difference. The huge actual difference is the dimension of the problem. So now the dimension of this PD is L, and it's not the same dimension of the original problem. So we get a reduction in terms of dimension, which is actually helpful in order to approximate this problem. But formally, what we are doing an orthogonal projection. How do we compute the orthogonal basis? That depends on the snapshots. That might be tricky. But once you get the basis function, you are able to project your problem and to reduce the dimension. So now, if we want to apply to a tree structure, remember that this is the tree structure. So we actually know our snapshots. So we can compute the tree as snapshots. Maybe we can use less control in order to have less nodes, and then we can compute the basis function. So the snapshot will be given by a tree. So this is very important, because usually when doing model of the reduction in the control setting, we have the control which is unknown. So this is not easy, and also the basis depends on the data. If the data have nothing to do with the control problem, then we are in trouble. So in this way, we know how to compute the snapshots. For instance, we use a few control and a large delta T. Then we don't have any restriction on the number of bases. We can use the singular values to understand how many bases we want, because our tree structure algorithm works in any dimension. So there are no constraints on the dimension of the basis, which actually happens when working on a structural grid. Then we can compute with a different time delta T, a different control space. We compute the reduced tree, and then we compute the value function. So in this way, also the pruning is easier, because we are doing a pruning in a lower dimensional setting. So it's easier to see when the nodes are. It's easier and faster to see when the nodes are close. Okay, we skip details on the pruning. So once you get the reduced tree, we can compute the reduced value function. Here, actually, there is no difference. The only big difference is that we have done a projection, but that is extremely helpful. What people have done in the literature is to use this approach on a structured grid, and that was already working. So now we have extended to this tree structure algorithm. And also, then we can compute the feedback control, which in our case really depends on the control setting, on the discrete setting. So we have to use the same discrete set of control for the for the value function, and then for the computation of the feedback control. If we want to change the feedback control, the control space, we need to use some interpolation, and this is something that we are currently working to improve the computation of the feedback control. Maybe I'll go to the test. So the pros, okay, are the computation of the snapshots that are built from the trees. There is the POD helps out to do the inefficient pruning. Again, we don't have to do projection. We don't have, let's say, we don't have to do interpolation. We don't have to do to set a numerical domain. We have no restriction on the dimension of the reduced problem. So now let's see how it works with a parabolic problem, 2D parabolic problem with a parabolic nonlinearity. Actually, this problem is known in literature because if we do a linearization and we use LQR, or I mean using an algebraic Caddy equation, that problem does not stabilize. So the linearized problem does not stabilize the nonlinear problem. So that is why this problem is interesting. And here, what we have worked with dimension 6. So essentially, here we have 1,000, and we got up to dimension 6. So here, this is the uncontrolled problem. So this is the evolution over time. Initial condition, time t equals 0.5, t equal 1. So you see that 1 is unstable equilibrium for this problem. Our goal is to reach the, no, actually 1 is the stable equilibrium. What we want to do, we want to reach the unstable equilibrium, which is 0. This is actually the focus of the control problem, that you see that here we have the initial condition, and then how the solution is actually steered to 0 when time goes on. So you see the difference at time 1 between the uncontrolled and the controlled problem. In terms of computation, for instance, here this is the control set. Okay, so here that means that we have 2 controls, 3 controls, 4 controls. So if we don't use model order reduction, you see how the time is increasing. And for instance, what is very interesting in my opinion is that if we use model order reduction, in order to get model order reduction, we need a full tree. So for instance, we compute the snapshot with 2 controls, and then we compute the value function with 3 controls. And you see that here it's 5 plus 19, this is 24. And this is actually, this coupling is actually 10 times faster than a straightforward 3-structure algorithm with 3 controls. So this is why also model reduction is interesting. So in terms of speed up of the approximation. Also, you see that after 4 days, we have to stop this approach with 5 controls. Here we got something in a decent time. And then the approximation, I mean, using POD or without POD are exactly this, provide exactly the same results. The big advantage here is that the time, the CPU time, and as expected, the cost function decreases, increasing the number of controls. We also have done Burgers equation. Here, Viscous Burgers equation. Of course, we have a viscous term. This is the dimension of the discretized PDE. So this is very, very large. And then here you see the difference. Again, we want to go to 0. Okay. This is lower, of course, but you see that the difference here between uncontrolled and controlled problem. And also the cost functional, if we use 3 controls, is a little bit smaller than using 2 controls. This is how the controls look like. Of course, here you see the big difference between uncontrolled problem and the controlled problem, which is always interesting to have. And then if we apply model reduction, in this case, we have used 8 basis functions, so in dimension 8. And then as expected, we get something which is very close to the unreduced problem. And also I want to mention that without model reduction, we were not able to do with the approximation with 11 controls, because the dimension of the trees is increasing, of course. And the pruning without the model reduction is also harder and very slow. So I'm going to the conclusion. Maybe it's interesting to see how the CPU time change, increasing the number of controls. You see from 2 to 3 controls for the full. This is way slower than using PUD and 11 controls, you see. So model reduction is important for having faster method and also feasible, I would say. So to conclude, the presentation of today was about tree structure for approximation of finite horizon optimal control. So very important was the pruning in order to solve the problem. Without not so many details, but I also mentioned that we were able to do high order method. We are actually able to solve this problem for any dynamical system and any cost function. So it doesn't have to be linear dynamical system. It doesn't have to be a quadratic cost function. And also, the coupling with PUD also gives some efficient, more efficient algorithm. And this is a list of references for this talk. And with that, I would like to thank you for your attention. And if you are interested, you can visit my website where all the papers are there and all the information. So thank you very much.